Evaluation measures are the foundation behind many of the biggest tech companies in the world. Many of these companies have publicly stated that a big part of their engagement is thanks to well implemented information retrieval systems. All of these systems rely on retrieving relevant information from some sort of database. These evaluation measures are how we can understand whether our retrieval performance is good or not. Evaluation measures are split into online and offline metrics. Online metrics can only be measured with a deployed product. Usually this begins with A/B testing. But before we even reach the stage of A/B testing, there is another step. Another set of evaluation measures that we call offline metrics. These are critical because they help us predict our retrieval performance before needing to put it in front of users. Now, an organization should always use both online and offline metrics, but offline metrics are the starting point, and that's what we're going to focus on in this video. We are going to have a look at predicting the performance of an information retrieval system before deployment, before A/B testing, before any of that. Now, there are many different types of offline metrics, but some of the most popular that we are going to focus on are recall at K, mean reciprocal rank, the mean average precision at K, and the normalized discounted cumulative gain at K. All of these metrics at first glance might seem complicated, but as you will see, they're very simple and incredibly useful ways of measuring the performance of our systems. Now, within offline metrics, including those that I just described, we have a separation into order unaware and order aware. This refers to whether the order of the results has any impact on the final score. In order aware, the order of results doesn't really make a difference, whereas with order aware, they do. Now, we'll see a few examples of this throughout the video. So if it doesn't make sense yet, don't worry about it. We will cover all of this. Throughout this video, we are going to be using a very small data set of just 8 images. Now, in reality, you will typically be working with millions or even billions of items. So this is a very simplified version, but it's ideal for understanding how each one of these metrics works. So in this case, our query is cat in a box, and we may return any 8 of these images in any particular order. Of course, some of them are relevant and some of them are not. And we can see those relevant results here. So the actual relevant results refer to those results that we would like to return. Okay, and everything else is not relevant to us, so we would rather not return those results. Now, when evaluating the performance of our information retrieval system, we are going to be comparing actual conditions to predicted conditions. Now, an actual condition refers to the true relevance of an item in the data set. So our actual relevant items here, their actual condition is positive because they are relevant. And for the other ones that are not relevant, their actual condition is negative. And we want to get our predicted conditions as close as possible to these actual conditions. The predicted conditions are what is produced by our information retrieval system. Now, the information retrieval system may predict something like this. So say we ask the information retrieval system to return 2 items. It may rank everything, and the top 2 items that it believes to be the most relevant to our particular query, cat in a box, are here. We have number 1, which has a predicted condition of true, which is what you can see over here with this P. Okay, so that P hat that you see means that the predicted condition is true. But we can also see that there's a negative. Okay, and that is because the actual condition of that item is false. It is not relevant to us. Okay, so we get this false positive. So there's negative, actual negative, and predicted positive. On the other hand, we have this other returned item, and this is a good result because we have a predicted positive and an actual positive. So that's a true positive. And we can also see down here we have these other items. So again, another good result. This is a true negative because the actual condition is negative, and so it's a predicted condition. And if we go a little further, we have some negative results, although you can't really see the box here. It is, you can just see it in the image there. This is a false negative because the cat is actually in a box. Okay, and we're predicting it, or the information retrieval system has predicted this is not relevant when it is actually relevant. So just remember, we have the actual conditions, predicted conditions, and we have positives or negatives based on those two forms of conditions. Now, with that, we can move on to our first metric, which is recall at k. Recall at k is pretty simple. We have the true positives, which we just described, divided by the true positives and false negatives. So what does that mean? We take a look at the predicted positives that are also actual positives, so the good positively returned results. Okay, that's what this PP is. And we divide that by the total number of actual positives in the entire data set, whether it was returned or not. Okay, so here they were returned, here they were not. That's all the recall is. It's relatively simple. So let's have a look at this. We have 3 items that should have been positive in this retrieval process, but they were not retrieved. Okay, they're the false negatives. So we add them to the denominator of our recall formula, and then we have 1 true positive. So one that was an actual positive result, and it was also predicted positive, which is good, but it could have been better, of course. So we add that to the denominator as well, and also to the numerator. So we get 1/4. So 0.25 for our recall at 2. Now, it's a little bit unfair because even if this was a perfect retrieval system, there are 4 actual positives here, and we're only returning 2 items. So the best it can score is 0.5. But that is just how the recall metric works. Now, let's have a look at how we would calculate that in Python. So we just create a recall function here. All we're doing is taking the actual items, the predicted items up to the top k. Okay, so before we had recall at 2, so in this case k would be 2, and we simply do that calculation that you saw before. Okay, nothing complicated there. That's our recall function, and all I'm doing here is saying, okay, these are the actual results, and these are up to the max of what we could predict. Okay, because what I'm doing here is going through and calculating this for all of the possible k values up to the number of items we have in the data set, just so you can see how recall works. So at the lower k values, recall scores a lot lower than does at higher k values. Now, if you have a pretty low k value and your system is still performing well, that's pretty good news. But if you increase your k value a lot, you can kind of cheat the system, because here we're getting a perfect recall score, and we know that our performance is not perfect. And that's obviously not ideal. And another problem with recall is we could swap in here, we could swap item 1 and 2. Okay, so we could be predicting number 2 as our top result. And recall, at least recall at 2, would still return us the same score. And depending on your use case, this may or may not be a problem. If it's important for you to retrieve the most relevant results at the top of your retrieval list, then this can be a problem. Okay, if it doesn't really matter, if you're just returning, let's say, the 10 items and you just need one item to be, the one relevant item to be within that 10, you don't really care where it is, you can go ahead and order unaware metrics like recall will work perfectly fine. But if you would like that one item to be scored at rank 1, then these order unaware metrics become a problem. So moving on to order aware metrics, we will start with the mean reciprocal rank, or MRR. MRR has a few advantages over recall. First, it considers the order of our returned results, as you will see that in a moment. And it also considers multiple queries, so we're not just relying on a single query in the case of MRR. So if we take a look at the formula here, there are a few things to consider here. First, we have the reciprocal rank, which is what you can see over here. Then we sum the reciprocal rank for each query, Q, from Q1 to the total number of queries, which is a capital Q. And then we take the mean by dividing this summed value by the number of queries that we made. That's how we get MMR, but we'll go through and break that down a little further in an example. So we start with these 3 queries. We have cat in a box, white cat, and dark cat. So queries 2 and 3, similar but slightly different to query 1. Now the data set is the same, so we're still returning all of the same items, we're returning them in a different order. So we first need to calculate the rank reciprocal. The rank reciprocal is the 1 over rank Q that you saw before. Now what this does is returns the rank of the first relevant item in the rank Q position. That's what rank Q means. Okay, so for your query Q, it returns the first relevant rank. So in an ideal scenario, this would be 1. So if we take a look at query 1 over here, the first relevant item is in rank 2. So that means here that rank 1 for query 1 is 1 over 2. Okay, so we get 0.5. Over here, we get that ideal scenario where it is returning a relevant item at position or at rank position 1. So we get 1 over 1. And then over here, we get a worse result. So we have to go all the way down to rank 5 to find the first relevant item. And that means here we have to do 1 divided by 5. So that's what the rank reciprocal part of MR is. And then we need to sum all of those together. Okay, so we have all of those, and that leaves us with 1.7. Okay, but that's not everything. We still need to divide by the total number of queries. So we have 1.7 divided by Q, which is 3, because we made 3 queries, which is equal to 0.57. Now, how does that look in Python? Again, it's pretty simple. We're just going to replicate what we just did. So we have the actual relevant results. Okay, we would run those, and then we'll come down to our calculation. We have a total of 3 queries here. So our Q value, the number of queries, is 3. And then we're just going to loop through each of those queries. We're going to make our query, and we're going to see what the first relevant result is. Okay, so the first relevant result is going to be 2, 1, and 5. Okay, and we see that down here. And then all we do is calculate the average reciprocal based on the number of queries we made, which is 0.57, which is the same as what we got before. And now we can move on to the mean average precision. Now, mean average precision, or MAP, is another popular order aware metric. It has a bit of an odd name. It's a mean of the average precision. So the mean of an average, but it does make sense, as we'll see in a moment. So we're going to start by just calculating the precision. Okay, so very similar to the recall, but this time we're only considering the items that we've actually returned. Okay, so the items that we've actually retrieved. And you can see that because we're just returning the predicted positives. Okay, and the denominator here is basically just k. Okay, so we can actually just do this, and that gets us our precision at k. So the number of relevant return results divided by the total number of return results. Now let's return to our cat in a box example. In this case, we are basically just adding 1 and 1 because we've returned 2 items here, so it's everything we've returned, e.g. k, and we've returned 1 relevant item, so it's just 1 over 2. So we replace this with k, and then 1 over 2. It's pretty simple. That's precision, and precision is the first component of mean average precision. But before we actually get to map at k, we need to go to average precision at k. Now, to calculate that, we take the precision value, which we just calculated, but you'll notice that we're using a small k here. And that's because we're going through every k value from 1, so precision at 1, all the way up to the actual k value that we have provided. So in our data set, we could go all the way up to 8, and we would calculate the precision at 1, 2, 3, and so on, all the way up to 8. And what this is doing here, this is called a relevance parameter, and it's looking at the relevance of a item at position k. So what that means is here we have our precision values that we have calculated, and this here is a lowercase k, by the way, not capital, and the relevance score for each one of these, if it is not relevant, is 0, and if it is relevant, is 1. And we go through all of those, taking the zeros for not relevant, as you can see here, and the ones as relevant. And we multiply all those together. So essentially what we do there is just cancel out all the non-relevant calculations and only calculate the precision where we have a relevant item, which is what you get here. So in the end, what we end up doing is we take all of those values. So you see 0.5, 0.5, 0.6, 0.57, which is the precision values that we get here. And we just divide them by the number of relevant results that we've returned, which is 4. And that is our average precision value. It's averaged over the possible k values. And you can see here that we've done this for 3 queries. Okay, so we have query 1, 2, and 3. Now, the mean part of mean average precision is simply taking the average over each one of these. And that's mean average precision. So how do we implement that in Python? We're going to use the same actual relevant items this time. Again, we're using Q like we did before, number of queries, and we have our predictor. The predicted is just the same for each one of our queries in this toy example. And we just go through and we calculate the precision first, which is pretty straightforward. We check the relevant parameter values. It's either 1 or 0, depending on whether the item at position k is relevant or not. And then we calculate the numerator value for AP. Okay, so the average precision. And simply divide that by the number of actual items for that particular query. Okay, and then we get these numbers here. And then all we need to do is take the mean of all those AP values to get map at k, which we have here. It's relatively straightforward. Now, the final metric I want to talk about here is a very popular one, and it's incredibly useful. It basically takes everything that was good about all the other metrics we've used and puts them all together. So this is called the normalized discount cumulative gain at k metric. It's another order aware metric, And we derive it from a few simpler metrics. So we start with the cumulative gain at k metric. So cumulative gain uses again this relevance parameter, but the relevance parameter is slightly different this time. It's not just 0 or 1 binary values. Instead, it is a ranking that is assigned to every single item for every single query. And they are assigned from a scale. The scale can vary. We're going to use 0 to 4 in this example. They are assigned a value of 0, which is less relevant, up to 4, which is the most relevant that an item can be for a particular query. Now, of course, this means that your data has to be labeled well, which is a disadvantage of using this metric. But if you have that labeled data, it's ideal because you have a lot more expressibility with your evaluation metric. So let's have a look at an example of how that might work. So going back to our earlier example, change it slightly. Now we're looking for a white cat in a box. We have two items that are super relevant because they are white cats in boxes. We have number 2 over here and number 5. They're both white cats in boxes. They're perfect. So the relevance score for those, we've assigned both of them a 4, which is the most relevant an item could be for that particular query. And then we have some other things. So let's go down. We'll go down to 3s. So here, number 4, we have a cat in a box, but it's not white. And the same for number 7. So it's still relevant. There's a cat in a box, but it's not a white cat. So it's less relevant. And we go down to number 2. So here, item number 8, and it's being ranked 2 because it's a dog in a box. So it's a domestic animal in a box. So it's sort of in the middle. It's kind of relevant, but it's not relevant at the same time. And then we get further away from that. So we go down to rank 1. So we have item 3 and item 6. Item 3 is just a box. Item 6, it's 2 cats. So it's kind of, half of what we're looking for. So in this case, it's less relevant. But neither of those are as irrelevant as a dog. Okay? In this case, the dog has been ranked as having a relevance score or rank of 0 because it's not a cat, it's not a box, it's nothing really to do that query other than being a domestic animal, which is not what we're looking for. So that's how that scoring mechanism works with all of the cumulative gain metrics that we're going to look at. And if we were to take that into our formula, we would get something like this. So we're summing over all k values. So we have k here up to the k of 2. Okay, so this is the lowercase k, this is the uppercase k. So we go 1 and 2. So we have a look at number 1. It's not relevant. It has a score of 0. So it's equal to 0. And then at number 2, it is relevant. So it has a score of 4. So our cumulative gain score in this case is equal to 4. Now, it's important to note here that NDCG, the metric, is order aware, but CG by itself is not. If we'd swapped those two items, as we have here, so we've swapped these two. If we go back to this formula, we are now doing 4 plus 0, which again is just equal to 4. So cumulative gain by itself is not order aware. To make it order aware, we have to use the discounted cumulative gain, or DCG metric. DCG adds one more component, which is this penalty value in the denominator. Using this penalty function, so this should be 4, and this should be 4 and 0. So if we take a look at these, we get 0 plus 2.52. Okay, so we score 2.52 in the case of the first query where we have the not good result in position in rank 1. Whereas if we have a good result in rank 1, we get a score of 4 because log to the base 2 by 2 is equal to 1 plus 0. Okay, so we get a score of 4 for our second query, which is better. And that's great because we're returning a better score. Now let's have a quick look at how we can calculate the DCG in Python. So we start by importing log to the base 2 from the math library. We have the same relevance scores that you saw before, so that's the rel k values. And we just go through those and we calculate the cumulative or discounted cumulative gain using rel k and our penalty function there. Okay, and you can see as it increases, because it's cumulative, the DCG also increases. Now, one problem with DCG, as we've just seen, is that the values don't really have any range because it depends on the relevance rankings or the range of relevance scores that we've assigned. In this case, we use 0 to 4, but you could use 0 to 100 if you want. It's a bit excessive, but you could do that. And in that case, the values that you're going to get out of this are going to be completely different than if you use a range of 0 to 4, which makes interpreting these numbers very difficult. So that's where the normalized DCG comes in. So the normalized DCG or NDCG uses another DCG metric called the ideal DCG to normalize these values to within a range of 0 to 1, where 1 is basically perfect and 0 is terrible. Now, to calculate the IDCG, all we need to do is reorder all of our ranked results into the ideal order. So those results that have the highest relevance will be ranked first, and it would go through in terms of relevance score. And then we just calculate DCG again using that new order because that is the ideal DCG. So using our earlier example, we have two items that are both ranked at 4. So we cross these values out, and in this case, we're going to use 4 instead. And we would get a value of 4 plus 2.52. So the ideal DCG is equal to 6.52. Now to calculate that in Python, it's incredibly simple. All we do is sort all of our relevance ranks beforehand using reverse equals true and do the exact same thing, calculate DCG. And using that, we get these values. So IDCG at 2 is equal to 6.52. And with all those calculations done, we have our DCG and our IDCG, and now we can calculate the normalized DCG, which is simply DCG divided by the ideal DCG. So for our DCG value, we got, using query 1, of 2.52. And our IDCG is 6.52. And that leaves us with a not too great score of 0.39. I'll switch back over to Python again and see how we would do that for all of our k values up to 8. So running through that, what I'm doing is calculating the ideal values here and also the normal discounted or DCG values and dividing DCG by IDCG, and then we get these values. Okay, so you can see over time as we include more items in there, the score does improve, but it never gets to perfect because this is not a perfect or ideal ranking of all of our items. Now, NDCG is a great offline metric because it really prioritizes for highly relevant documents. But at the same time, we do need that more complex training data or label data in order for this metric to actually work. But if we do have that data, this metric is perfect. Now, That's the end of our metrics. It's all of them. So we've covered recall at K, we've covered mean reciprocal rank, we have covered mean average precision, and we have also covered NDCG. You can use a few of those in your information retrieval systems to evaluate your performance. And you really don't need much else other than that for your offline metrics. In the case of Spotify, for example, with their podcast search, they use mean reciprocal rank at 30 and also recall at 30. And that was they were there on offline metrics. They didn't use anything else other than recall at 1 for their in-batch evaluation. Now, of course, these metrics still need to be supported with online metrics during A/B testing and whilst you're actually in production. But these really get that first step of preparing an information retrieval system that is the best it possibly can be without needing to deploy it to any users. And that's ideal because you will get the best information retrieval system you can if you use these offline metrics well. So that's it for this video. I hope this has been useful. So thank you very much for watching, and I will see you again in the next one. Bye.